nice to see you again. We're finishing this introductory series of lectures on physical processes. In the third lecture of the series, we described the changes of phase in pure liquids and produced heating curves that incorporated these phase changes. Well, those curves will change if we dissolve a chemical in them. In this lecture, we will focus on the interesting changes that occur in pure liquids when we add a bit of solute to them. In the last half of the lecture, we'll change our focus and look at the solutes and how their chemical makeup determines if they'll be soluble in a water solvent or not. Very interesting things occur to a pure liquid if you throw a little something into it and it becomes a solution mixture. I want to focus on 3 changes to the liquid which now has become a solvent. The liquid's vapor pressure will go down, its freezing point will go down, we call this freezing point depression, and its boiling point will go up, we call this boiling point elevation. We won't be doing a lot with the vapor pressure lowering of the liquid right now, but we do want to spend a little time on the last 2 properties. These changing solvent properties due to the addition of a solute are called colligative properties, and we use these colligative properties to our advantage all the time. For example, we typically put a solvent like water in radiators to cool the engine in our cars. Antifreeze is mixed in, and the water's freezing point goes down so that cold winter temperatures can't freeze the liquid in the motor, preventing the water from expanding and cracking the engine block. And we've all seen the pictures of cars getting too hot and steam flowing from under the hood. Well, the idea of having a water solution rather than pure water is that the solution now boils at higher temperatures, so it won't vaporize when the engine heats up above the normal boiling point of water. And here's another one. How many of you have put a bit of salt in water before you boil and cook something like spaghetti or oatmeal? As well as seasoning the food, the salt in the water will elevate the temperature at which the water boils, and the food will cook at a slightly higher temperature and cook a bit quicker. At moderate concentrations of solutes, it's straightforward to calculate the change in the new boiling and freezing points of the solution mixtures. For now, we will limit our solvent to water. To calculate the change in the freezing point when we drop a solute into the solution, we use the simple formula shown, where delta Tf is the change in temperature relative to the normal freezing point of the pure substance in degrees C, or K since we're looking at temperature changes. M is the molality of the solute, where the molality is defined to be the moles of solute divided by the kilograms of solvent. And Kf is the unique freezing point depression constant for the solvent. For water, the value for this constant is minus 1.86 degrees Celsius divided by the molality of the solute. So, if we have a 2.5 molal sugar in water solution, what will be its freezing point? To figure this out, we simply multiply the freezing point depression constant for water by the molality of the solute in the solution, and we obtain a temperature change of minus 4.7 degrees C. We use the textbook regular rounding rules in the example. Now, water normally freezes at 0 degrees C at 1 atmosphere, but this solution will now freeze at 0 degrees C plus the change we just calculated, delta Tf of minus 4.6 degrees C. So the freezing point of this solution will be minus 4.6 degrees C. The boiling point elevation behaves similarly and has a comparable formula where delta Tb is the change in the temperature of the boiling point relative to the normal boiling point of the pure substance in degrees C or Kelvin. M is the molality of the solute again, and Kb is the boiling point elevation constant for the solvent. For water, the value of this constant is 0.512 degrees Celsius divided by the molality of the solute. For our 2.5 molal sugar solution, the boiling point elevation is calculated to be 1.3 degrees C higher in temperature than the boiling point of the pure solvent. The normal boiling point of water is 100 degrees C, but this sugar solution will boil at 101.3 degrees C. An aqueous solution is assumed to be a homogeneous mixture of a solute and a water solvent. An ionic compound like sodium chloride salt dissolves readily in water and conducts electricity. We know the sodium plus cation and the chloride minus anion undergo solvation or ion dipole interactions that separates the ions in the solution, making it conductive. In general, we also know that like dissolves like, and in the case of an ionic compound, the ion dipole interactions of the very polar H2O molecule with the charge of the ions help dissolve these salts. So for moderate conditions and dilute solutions, ionic compounds that tend to dissociate totally and are completely soluble in the water are called strong electrolytes. Sodium chloride is considered a strong electrolyte. One way to write the process of sodium chloride completely dissolving in the water, making an aqueous solution of the ions, is as follows, where we put the phase in parentheses next to the chemical. For solid, we use the small s, and for the aqueous condition of the ions in the water solution, we used AQ. The one-way arrow denotes a process going to completion from the reactants to the products. The equation we have written is called an ionic equation. Now, we all know that eventually we can put so much salt in the solution that it won't dissolve any more chemical. This overabundance of solute is called a saturated solution. In these solutions, we eventually get to an equilibrium state between the solid and the aqueous ions, where both phases exist in the solution. We're required to draw the saturated equilibrium situation differently than the ionic equation we wrote down before. The double arrow denotes that the products and reactants in this equation are now in equilibrium. So, be aware that when we use descriptions like strong electrolyte or solubility, we're using subjective terms to describe the system, and really the term only applies if we consider dilute solutions. For the rest of this lecture, the rules for solubility that we are about to discuss are assuming modest conditions and fairly dilute solutions. Two factors loosely dictate the degree of solubility of salts in water. As cations and anions get bigger, with the ions having expanded electronic densities, solubilities tend to decrease, and second, as the bonding becomes less ionic, something we could check out on a Kevlar diagram, the salts become less soluble in the water. It would be convenient for us to know beforehand if an ionic compound is soluble, insoluble, and even slightly soluble. For aqueous solutions, there are a set of guidelines and empirical rules that we can work with as starting points. These solubility rules give us some idea of the degree of solubility of many common ionic compounds in water. The rules for the solubilities of common atomic and polyatomic ions found in many ionic compounds, and the notable exceptions to the rules are given in the following table, and you need to be familiar with them. It will turn out later when looking at chemical reactions that to truly understand and predict the results of what is called precipitation reactions in water will depend heavily on how well we know these solubility rules. The most important solubility trend to always remember is that any salt containing an alkali metal cation, the ammonium ion, the nitrate ion, or the acetate ion are always soluble, without exception, in dilute solutions. Salts with the halides are also very common, so make sure you keep the solubility rule for that series in the forefront of your mind at all times. All halide salts are soluble except those salts containing the silver plus, the mercury 2,2 plus, or lead 2 plus metal cations. So a solid compound like lead-2 iodide, PbI2, dropped in water will more than likely not be very soluble and remain solid in the water. When studying this table, please note that the section of ions on top are mostly soluble and the section of ions on the bottom are mostly insoluble. And as I mentioned before, the salts are easy enough to recover from solutions sometimes if we boil off the solvent or let the solvent evaporate and let the salts crystallize out of the solution. That's why it's sometimes difficult to categorize the process of dissolving salt as either a physical or chemical change. It is a bit of both, I think. There is much more to learn about colligative properties and the world of ionic solutions. So take this lecture as it's intended, a nice introduction to what is a much deeper conversation on these topics. Remember, there's a whole internet full of information out there, okay? So be well, and we'll see you in the next video.